Purpose of this video is to go over AP Practice Problem C. In this problem, they talk about a chemical reaction that can be modeled by this function. They don't tell you what the function is, but basically the amount out is modeled by some function of time. And they tell us what those things are, that the amount that we're getting, which is the y value, is in grams, and that t is time in seconds. They also give us that at the start of the reaction, time 0, there's going to be 10 grams of substance. So that's going to serve as an initial condition. We have that time 0 gives us an output of 10 grams of substance. Once again, we still don't know what the function is, but they do give us its derivatives. They give us the rate of change. So the reaction's rate of change, change in substance over change in time, dy dt, is negative 0.02 y squared. Be careful with this because this derivative is not in terms of t, it's in terms of y, it's in terms of the output. So you can't just do a regular antiderivative to this. If it were in terms of t, to get the original function, you could just do an antiderivative. But because this is in terms of y instead, and not the independent variable, this needs separation of variables to be solved, which we'll see later. All right, so let's look at the problems that they want us to do. They want us to come up with a tangent line at 0, and then instead of just coming up with the tangent line, they want us to actually use the tangent line to approximate how much substance there is at 2. We don't have the original function, so we're not able to, at the moment, get what the actual amount is at 2. But if we get the tangent line, it should be a decent approximation, so long as we don't get too far from 0. Even 2 might be kind of far, but we don't know what the function looks like, so we'll just do what they say and hope that it's reasonably close. Part B asks us to see if this thing could be the original function. So we have the derivative. Could this derivative give us a function that looks like this, or come from a function that looks like this? The answer is actually going to be no. We'll have to say why. So I'll tell you why this can't be, and that'll get us a point for that. Part C wants us to actually solve the differential equation. So I mentioned we don't have the original equation. Well, with the initial condition and this derivative, we can work it backwards using separation of variables and solve the differential equation to give us the original function. And then lastly, and this gives a lot of people problems because of the wording. It says determine whether the amount of substance is changing at an increasing or decreasing rate. So it's asking us about how the substance is changing, whether its change is increasing or decreasing. So the problem I get is people see, oh, they want to know if the substance is increasing or if the substance is decreasing, and they think, oh, let me go to the derivative because that gives me the change of the substance, and this comes out negative, so it should be decreasing. But you have to be really careful with the wording. It's not asking me, is the substance increasing or decreasing? It's asking me, is the change of the substance increasing or decreasing? If I want the change of the change, I need the second derivative. So that's what's tricky about this. They're asking about if the changing of the substance is going up or down. So it's already the rate of change, and they want to know if the rate of change is changing upward or changing downward. So remember, a change of the change, the change is a change of the derivative. A change of the derivative is measured by the second derivative. So this is going to be answered by a second derivative, and we'll explain our reasoning that way. And like I said, this is very tricky because people tend to not realize it's talking about the change of the substance already. They think it's just the substance itself, and they go for the first derivative. But this requires the second derivative. All right, well, so let's start going through them. Part A, let's find the tangent line and use it to approximate. So they give us a point to estimate from, and they give us the input and the output. Now, keep in mind, t's playing the role of x. Don't let that confuse you. T's the independent variable. Y is the dependent variable, input, output. So I have the point that my line needs to go through because they told me put it through t equals 0. Well, the output will be 10, so I'm going through the point 0, 10. Now, in order to find the tangent line, I don't just need the point, but I need the slope. The slope can be found by the derivative. So I need the derivative at the point 0, 10. Now remember, the equation is in terms of y, not in terms of t. So I'm not actually going to use the t value in the equation, but I'm going to use the y value. So what is the derivative at that spot? It's negative 0.02 times t squared, or y squared, and y is the value 10. So I'm plugging in the 10 and calculating what that is. So the slope at that spot is negative 2. Once I have the point and the slope, I can write the tangent line. So this is point slope form. I did y minus the y coordinate 10 times the slope equals the slope times t minus the t coordinate. So you can use it in this way. If you decide that you want to put it in y equals mx plus b form, you could. It comes out as the slope's negative 2, so it'll be negative 2t. This won't matter, and you'll move the 10 over. So it would be y equals negative 2t plus 10. I wouldn't even bother doing that. You can use it in this form. But if you did that, you could also use y equals mx plus b form. So you get a point basically for getting the slope. Now the tangent line, you need to use the approximation for. So they do say approximate what the amount is, the y value is at 2. Now you don't have the original function, but you do have this tangent line. The tangent line should be reasonably close, so we'll use t equals 2 in the tangent line. Now if you do this y equals mx plus b, you can just put the same thing, put the 2 in for t. But in this form, you can do that as well. So I'm putting the 2 in for t, and then I just calculate. If you calculate this down, what's y? Y comes out as 6. So according to the tangent line, after 2 units of time, I come out with 6 units of substance. And I believe time was seconds. So it'd be 2 seconds. I end up with 6 grams. Now remember, this is an approximation. I don't have the original function. This is just what the tangent line tells me, and we're hoping the tangent line's close. All right, so according to the tangent line, I have 6 grams of substance. Part B was see if you can figure out if this graph is possible. I said in the beginning it's not. Here's why. Basically, we're going to look at that derivative. Y squared always comes out positive. Now, I should be a little better with my explanation here. Technically, y squared could be 0, so I didn't want to rewrite this, but it would be better to say that y squared is never negative, because technically, there is one exception to this. If it were 0, it wouldn't be positive. Basically, y squared is always positive or 0. So a better thing to say here would be, since y squared is never negative, basically that's going to be the key thing. This thing can't come out negative. And since this term is never negative, it's either 0 or positive. If you multiply it by a negative number, you're going to get that that derivative is always 0 or negative. I snuck in the 0 there, just to be precise. So because of this fact about y squared, the derivative has to be negative. Since the derivative is always negative, so that's what I'm saying here, since the derivative is always negative, the original function should always be decreasing. Because remember, if you have a negative derivative, you're on the decrease. If we take a look at this picture, though, it decreases for a while, but then it increases over here. The original graph cannot look like this because basically the slope has to always be negative, the function should always decrease, and this has positive slopes and has increase on it. So it's not possible. So basically I said since the function shown has a section of increase, it can't be the function we're looking for. It can't be f of t. There are other ways to answer this. This is the most obvious one. All right, because it basically just goes back and finds what happens with the derivative and shows that the picture doesn't have the right characteristic. All right, let's look at part C. Part C says, finally, let's find that function. What is instead of the tangent line approximation, what's the actual function for the amount of chemical based on time? So we have to solve this differential equation, and they give us initial conditions. So we need to solve this by separation of variables. Remember, we can't just do this thing's antiderivative because it's not in terms of t. The derivative is in terms of t, but this part's not in terms of t, so we need to do separation. So let's look at the work. This one's the bulk of the points in the problem. To do separation of variables, you need to put the y's with the dy and the dt with the t's. Now, there are no t's, but I'll still move it to the other side anyway. So the y squared is going to divide over, be 1 over y squared dy. I'm going to leave this number here. You could move the number over, but it just makes it harder. I'd keep it on the side with the independent variables. So I'm going to multiply over the dt, And this thing, then that'll get you a point for the separation. You then need to get the antiderivatives to get rid of the differentials. So if we take the antiderivatives, I simplified this to be able to do that. Remember, 1 over y squared. Be careful not to put a natural log, because it has a power with it, it's y to the negative 2, and we'd use the power rule backwards. So when we take these antiderivatives, the power rule backwards on this says add 1 and divide by the new number. Well, that gives me negative 1 and divide by negative 1. So the antiderivative of y to the negative 2 is negative y to the negative 1. The antiderivative of a constant just puts the variable on it, where in terms of t here, so when you take the antiderivative with respect to t of a constant, that constant just gains the variable t. So my antiderivative for negative 0.02 is going to be negative 0.02t, because we did it with respect to t. I'm going to put the plus c, because when I do the antiderivatives, I need a plus c. I'm going to put it on the side where I'm not solving for it. I want y by itself, so I'll put the c on this side. All right. Basically, you get a second point for the antiderivatives. So now we're up to 2 points. From here, I want to get the c value to get the third point, but I got to do a little bit of adjusting here to make it a little easier to work with. So basically, I got rid of the negatives on both sides. Dividing the negative away makes that positive. Dividing this negative makes it positive. Now, you could go technical and go, well, shouldn't the plus c become a minus c? But remember, we haven't even found what c is. If we modify it, it's still just another constant, so we don't technically need to change this. If you do and you're careful with it, it'll come out with the same answer. But basically, this number is still just some number. I haven't found it yet, so I'm just going to leave it as plus c. Now that I have this equation, well, y to the negative 1 is 1 over y, and now this is going to be easier to plug into. So now I'm going to use my initial condition. My initial condition is that at time 0, the amount of substance was 10. So t is 0, y is 10. That gives me this equation. I can solve for c. This zeroes out, and c equals 1/10. So now that I know c is equal to 1/10, I'm going to go back to my original equation and plug that in. I get 1 over y equals 0.02t plus a tenth. Now the last point is they want y by itself. So I need to get this function with y alone. It's a little tricky because you want to flip this over, or if you want to cross multiply, you can do that too. Problem is that you can't do it with this addition here. It's going to make it trickier. So I'm going to combine this into one fraction. That way I can just flip them over. Or if you prefer to cross multiply, you can do that as well. So from here, how am I going to get the y alone? Well, I'm going to get this as one fraction. 0.02, I'm going to use the fact that this is the hundredths place. This is 2/100ths. 2/100ths can be written as a fraction, 2 over 100. So since this is 2/100ths t, I might as well get a common denominator with this. Well, it's 1/10. If I multiply top and bottom by 10, I get 10/100ths. So now I have a common denominator. Essentially, this t can go on the top. I got 2t over 100 plus 10 over 100. Put that over the common denominator, I get 2t plus 10 over 100. So now I'm going to skip the cross multiplying, because basically I can just reciprocate both of these. If I reciprocate 1 over y, I get y. If I reciprocate this fraction, I get 100 over 2t plus 10. Since the y is now by itself, this is an answer. I did simplify it just in case, because 2's go into both of these. You could simplify it down to 50 over t plus 5, but you don't have to do that. Basically, getting y by itself is the last point. So notice bulk of the points for part C, one for the separation, one for the antiderivatives, one for finding the constant, and one for getting the y by itself. All right, so then the last question was the one I said was pretty tricky because you have to read it carefully. Once again, determine the whether the amount of substance is changing. So is the change happening at an increasing rate or decreasing rate? So is the change increasing or is the change decreasing? And basically, if we want to know how the change is changing, we need the second derivative. So that's what I put. So to find how much the rate of change is changing, whether that rate of change is increasing or decreasing, we need the second derivative. So to find the second derivative, I need to take the first derivative and do the derivative with respect to t again. So I need to basically do d dt to both sides of this, is how I started. So I took the original equation. Basically, I'm taking the derivative with respect to t on both sides. When I take the derivative of the derivative, I get the second derivative. When I take the derivative of this thing, I have to be careful because it's with respect to t. So I am going to do the power rule here. The 2 times negative 0.02 is going to give me negative 0.04 y, but since the variable didn't match, the chain rule spits out a dy dt. So the second derivative is negative 0.04 y times the first derivative. Now I know what the first derivative is. It's this original expression in here. So I'm going to replace the dy dt with what the original value of it was, which was negative 0.02 y squared. So now the second derivative, with that first derivative plugged in for, simplifies down to positive 0.0008 times y cubed. So you get a point for calculating the second derivative. You can actually leave it this way, but to make my argument, I wanted to point out that this is always going to be positive. Why is that the case? Well, y is the amount of substance. The amount of substance can't be negative, so y is always going to be positive. Therefore, y cubed is always going to be positive, and this number is positive. So that's basically what I explained here. Since y is the amount of substance and is always positive, and once again, could be 0, but it's not negative is the key thing. 0.00083y cubed is going to be positive, and since the second derivative is positive, the substance is changing at an increasing rate. So the second derivative is positive. That means the rate of change of the rate of change is positive. If something's changing in a positive way, it's increasing. So the rate of change is increasing because the second derivative is positive. All right, the second derivative is talking about the rate of change of the rate of change. So the rate of change of the rate of change is increasing. All right, so that justifies my answer is the substance is changing at an increasing rate, that its rate of change is going up, and because the second derivative is positive. So that's giving you a point for that explanation. So that's all 9 points, and that's how you can get it. Yet another one of these differential equation problems. So once again, if you're covering, try to cover all your bases for what they may ask. This basically has, doing the tangent line and actually using it to do a linear approximation. Some information about using the derivative just to analyze a function, solving a differential equation, and understanding how to get the rate of change of the rate of change. All right, so hopefully that helps get you more points on your exam, and join me next time for good old AP Practice Problem D. See you then.